In this video, I'm going to be covering challenge number 15, ABI Smuggling from Damn Vulnerable DeFi. In this challenge, there's a permission vault with 1 million DVT tokens deposited. The vault allows withdrawing funds periodically, as well as taking all funds out in case of emergencies. The contract has an embedded generic authorization scheme, only allowing known accounts to execute specific actions. The dev team has received a responsible disclosure saying that all funds can be stolen. Before it's too late, rescue all funds from the vault, transferring them back to the recovery account. So this is a really interesting challenge. I really enjoyed it when I went through it. So let's go ahead and take a look at the contracts. So we're given two contracts in this challenge. It's actually one challenge contract, but one just implements the other, where we have the self-authorized vault and then the authorized executor. So we're going to go through the self-authorized vault first. As you can see, it is an authorized executor, so it implements that contract. So we're going to have a look at that as well. We get two variables, the withdrawal limit and the waiting period, and the last withdrawal timestamp. A couple of errors, a new modifier, which is only this, which looks like if the message.sender doesn't equal this contract itself, revert. So that's saying please only if this can only call itself. We have a withdraw function, which allows to send a limited amount of tokens to a recipient every now and then. We've got a token, a recipient, and an amount. So looks like this is only this as well. So only the contract can call this withdraw itself. The amount, if the amount is greater than withdrawal limits, we've got some validation here. It looks like there's a time waiting period that we need to wait before every time we can withdraw. So if the current block.timestamp is less than or equal to the last withdrawal timestamp plus the waiting period, and that waiting period was 15 days, then revert. Otherwise, we can transfer to the recipient the amount that is we want to send. And this amount is 1 ether. So we can only take out 1 ether every 15 days. There's another function here called sweep funds, which is, again, only this and follows the safe transfer. And that's fine. So that will basically take all the funds of the specific token and sends it to the receiver. We have a helper function called get last withdrawal timestamp, which will return that. And we also have a function called before function call, which is an override, which is implemented from the authorized executor, which is just verifying that the target is that the target is equal to the address. So if it's not equal to the address, then we're going to revert. So again, it's kind of similar to that, only this modifier. Okay, cool. So we've got this vault and we can withdraw 1 ETH and we can also sweep funds apparently. So let's have a look at the authorized executor. Again, it's a reentrancy guard. We've got some initialized function variable here, a mapping of permissions. So this is interesting. So it's an action identifier to allowed. So this bytes32 is going to map to a Boolean, which will basically tell what permissions each individual is able to do. So we'll cover that in a little bit. A couple of errors and events here. And so this is interesting, set permissions. So we get an array of byte32s called IDs. And if this contract is already initialized, then revert. So if this is probably set up in the initialization, and we do a for loop for each of the IDs. In each of these IDs, we set the permissions IDs value. So each byte's 32 equal to true. So this is setting the permissions. So it'll be interesting to see what these IDs actually are or where they're calculated from. Initialize equals to true, and then it emits that. And this is really the interesting part of this challenge is this execute function. So this performs an arbitrary function call on a target contract if the caller is authorized to do so. We have a target, we have action data as the two parameters here. It's non-reentrant and it returns some bytes. So how does this work? So we can see that the action data is actually call data. So I'm assuming that that's going to be calling some other function since this is execute on a particular target. So we have a bytes for a selector, a call data offset, which is hard coded at 4 plus 32 times 3. We then have assembly. So this is going to call data load starting from the call data offset. So this is going to get the call data from the execute function. So what was sent with the transaction for like the data that was sent with the transaction to call this execute function, starting at the call data offset and then reading 4 bytes because this selector is only 4 bytes. So this looks like it's reading the function selector of the action data. So that's what this is saying here. So if you don't know what the function selector is, a function selector is a 4-byte kind of signature for every single function in a contract. So this execute function will have a specific function selector, and it's unique by its name and the parameter types that it takes. So it takes the name and the parameter types, and then it can generate a signature from that, which is 4 bytes long. So when you send a transaction to a contract, those first 4 bytes tell the contract which function that you want to execute. We then read the permissions. So this permissions is what was initialized before. It gets the action ID given the selector, so that's the function selector, the message.sender, so whoever's sending this message. So this is actually not only this. So we, as an external player or external account, can call this function. And also the target, so where we're going to call this. So if we go further down here, we can see it does a before function call on the target and action data, and then it does target.function call on action data. Now, the reason that we can do target.function call, because target is an address, is because we're using the OpenZeppelin address utility library. So it's using address for address here. So that kind of adds some more functionality to that base type. And we do a function call with the action data. So let's have a look at what this get action ID is. Now we saw this before function call, which is overridden in the self-authorized vault. So this is basically making sure that the target is the contract itself. So we can only call the contract itself is what this is enforcing. The get action ID is going to take the selector, the executor, and the target. So this is the selector, the sender, and the target here. And it's going to hash them all together by ABI encoding them all together, hash them all together, and that gives you a unique key for what action you're trying to do. So given the executor, the target, and the function that you're trying to call, you are given a unique key. And if you have that permission to do that function or execute that function, then that'll go ahead and do the target function call. Cool. Okay, so that's the contract. This looks pretty interesting. So let's see what we have to do. We have to steal all the funds from the vault. Actually, it's not steal all the funds. We have to transfer it to a particular address. So given the context of the challenge, we need to return all funds, transferring them back to the recovery account. So let's go ahead and have a look and see how this is set up here. So the initial token balance has got a whole lot of ether in it. So if we're going to withdraw, doing the withdraw function, doing 1 ether every 15 days, that's going to take a very long time. So there's probably a better way to do this. We've got the deployer, the player in the recovery account, deploys the token, deploys the vault, the self-authorized vault. So this is interesting here. So the deployer permission is going to get the action ID of this particular hex value. Now, if you have a look at the function signatures for this contract, you'll notice that this action value, and I'll show you how to get that in a second when we start writing the code, but this is actually the function signature for sweep funds. So this is the one that will allow you to transfer all of the tokens. But this permission is actually given to the deployer. So we're not going to be able to get access to that. What we are able to get access to is this function, and this function is the withdraw function, which isn't very helpful because we're only allowed to withdraw 1 ETH every 15 days. But nevertheless, we are given that permission because it's given to the player. Those 2 permissions are then set in the vault, set permissions passing in those 2 unique action IDs, and then it does a whole lot of verification, transfers some tokens into the vault, and we're ready to go. So all we have for this is essentially we have permission on this vault to call withdraw and nothing else. And we need to steal all the funds from this and send them to the recovery account. And let's have a look at what we need to do. So again, the balance of the vault needs to be 0, the balance of the player needs to be 0, and the balance of the recovery address needs to equal the vault token address. Now these are all the DVT tokens, not Ether. So how do we exploit this? So let's have a look at the contract and see if we can start theory crafting what potentially could be going wrong here. So the first thing that I want to look at is this sweep funds function. This is basically our exit that looks like if we can execute this, then we can steal the funds from the contract. So how do we call this function? Well, the sweep funds function can only be called by this, which if you kind of think back to only this is a contract that can only call itself, or this function can only be called by the contract it's defined in. So the only way that we can get the contract to call another function of itself is using this execute function. So let's take a look at this execute function. And of course, we can actually execute this function. So we can call this function because it's external and it doesn't have that only this modifier. So let's have a look, a bit of a closer look on how this particular function works. So again, we've got the selector that reads the first 4 bytes of that call data offset, checks the permissions, and then that before function call. So for example, if we wanted to call this function and we wanted to call the withdraw method, we would pass in the parameter, the target would be the contract address itself, and the action data would be the function selector, followed by the parameters needed to call that function. Now, in our case, the withdraw function has 3 parameters. So you would pass in the token, the recipient, and the amount. So what that would look like in terms of the call data that is being called, including the call data for the execute function. So there's the call data for the execute function, which includes the target and the call data for the action data. So the action data is contained within the call data of the execute function. So I have a little diagram that in my write-up on my website, which kind of describes this. So this is the diagram of what the call data would look like for a normal call. So you would have the function selector. Now this function selector is for the execute function. This is the unique signature that defines the execute function. We then have, so that's 4 bytes. And then I'm starting the bytes here at 0 because usually you kind of ignore the first 4 bytes of the function selector, and everything after that is kind of referenced from the data portion of it. And I'll explain to you why that happens in a second. So starting at byte 0, and it's been prepended with the function selector, we have the target address parameter. So again, coming back here, the first parameter here is that target address. Now, because addresses in Ethereum are known 20 bytes long, we can just put this in. So each kind of section here is a 32 byte section. So this is 4 bytes, 32 bytes, 32 bytes, 32 bytes, and then more 32 bits of 32 bytes. So because this is always 20 bytes, we know that we can fit this in this 32 byte block and put in that target address parameter here. Now, the interesting bit is when we look at the bytes and the action data parameter. So this is this next parameter here. Now, what you'll notice here, it says action data data location. Now, because bytes is a dynamic type or dynamically sized type, that means that there is no specific size that we know that this parameter will fit within. And it's as opposed to the address parameter type, which has an address size of 20 bytes. Which will definitely fit in that 32 byte section. We don't know how long this bytes is going to be. It can be varied between different calls and, depending on which action data that we want to provide. So during this, and by the way, this whole thing is called ABI encoding. This is, how things are encoded for Solidity. And what I really recommend if this explanation doesn't really help too much, is having a look at the ABI spec in the Solidity docs, and this will tell you a little bit more about how how it all works and how the ABI specification works. So for dynamically sized types, the action data is actually a pointer. So this is the data location of where the data portion of the bytes starts. Now, the reason this happens again is so we know that once we read this, we can then go to that portion of data and start reading from there. So then if there was a third parameter in this case, the third parameter would go after this one. So each individual 32 byte section would have the parameter that corresponds to it. If it's dynamically sized, then it's going to be pointing to a later section in the ABI encoded call data. So again, this is starting at the 20th, this is in hex, right? So hex 20th byte or the 32nd byte. So this data location is actually going to be pointing to 0x40, right? And so that's going to be the 64, no, this is the 64th. No, yeah. Sorry, the 64th byte. So the 64th byte is going to be the start. And so the first 32 bytes from the data portion that this points to is going to be the length of the bytes. So now once we go here, we're going to go, okay, yep, we want to read this many bytes. So whatever our action data is, we've encoded that this length is going to be how much data that we have. So, say the action data length is 120 for some reason. We then go to the next byte, or like 32 bytes, and then we start reading 120 bytes. And then we go through the actual data, and stop reading 120 bytes, and that is all loaded into Solidity, and that is then passed in here. So now knowing that, let's have a look at why this specific number has been put here. So again, this selector variable is reading the selector of the action data call data. So if we have a look back at our kind of diagram here, we can see that there's 4 bytes here for the function selector, 32 bytes here for the target address parameter, 32 bytes here for the action data location in the call data, another 32 bytes for the action data length, and then the actual action data is going to be starting here. So 4, 32, 32, 32. 4 plus 32 times 3, right? And so this action data also has the function selector at the start here, followed by the regular data. So this is a call data from within the larger call data of the execute function. So these first 4 bytes here are the function selector of the action data. And so that's why the call data offset, right? When we read the call data, it's starting from that call data offset. So it's starting from here, reading 4 bytes and loading that into the selector variable. And that's how we get the function selector for the action data. So it reads that and then starts calculating the permissions from it. So where's the exploit here? How do we actually exploit this? This looks a bit weird. Well, from there, we kind of think back to how this ABI data was encoded. And we made an assumption, and that assumption is that this ABI data is always packed perfectly and correctly. This data location will point to the start of the data, or the data length, right? And then the data comes immediately after that. But what if it didn't? Can we change that? Is that a thing that we can do? Would that break Solidity or something like that? Well, let's imagine that this data location, instead of pointing to hex 40, we started at hex 60. Let's shift everything over by 32 bytes. So we'll put like random data in this hex 40 to hex 60. Then we'll have the length, and then the data comes after that. So let's have a look at what that function would then start to look like. So same function selector, same target address parameter, but now this action data is now pointing later in the call data. And so this continues on to 40. So we have random data here, and then the action data length, and then the action data. Now, this is cool because this will actually be valid call data. Kind of. There's 2 kind of problems that we need to address though. Solidity doesn't care if your call data is too large or is too large from what it is actually expecting. But it does matter if it's too small. But in this case, we're going larger rather than smaller because we're adding in unnecessary random data. So this is valid call data. Except the problem is that when the contract tries to read the 4 bytes at this hard-coded offset, right, it's going to start hard-code at 4 plus 32 plus 32 plus 32 starting from here. So it's going to read the first 4 bytes here. Now, the action data length is probably going to be around 100 or 120 in those numbers. So it's going to be 0x0000000000 all the way to like 120 right at the end. So what that means is that when it reads the first 4 bytes here, it's going to read 0000 as the function selector, which is not what we want because that's still not a permission that we have, right? So what we need to do is somehow get the permission that we are able to have, which is this 0xd9caed, to be located at this position here at 0x60 and still have everything else work. Because then in our actual action data function selector, we could then call with the sweep funds method. Now, why that works is because this is just data. This is just random data that we put in. But in the actual action data, when we call it, where is it? Execute, right? We're doing a target.function call with the action data. It's not using anything else. And that action data can have whatever it wants. The action data is not calculated in the get action ID. So again, the exploit here is that this is hard coded and it's supposed to expect the data to be starting at this offset when we can change that and we can have control of that. But we still haven't solved a problem. So say we put in that function selector that we do have access to here. Well, that's just going to mess up our action data length, and that's going to give us an invalid parameter because this is going to be an absolutely ginormous number if this is left aligned with the function, with the action data length, and it's going to be reading too much data, it's going to run out of data, and it's going to give us an error. So this won't work either. So what if we just shifted over it again by another 32 bytes? So then we have a look at this function diagram here. So we have our function selector, which is for the execute function, the target address parameter, which is the contract address. But now the action data location is now going to be pointing to hex 80. Now this is going to be starting down here now. So this is going to point to this function here. Now the next 32 bytes can just be random data, doesn't need to be anything. The next 32 bytes is now where where the function is going to read the first 4 bytes. So if we put the first 4 bytes of this here and then just, put zeros for the rest of the 32 bytes in this slot, then when the contract reads the first 4 bytes, it thinks that this is the selector that we're calling. But then when it actually retrieves the action data, it's going to put the action data here with valid action data length, right? Because we put that in as what we want it to be, doesn't need to be changed for anything else. And then the actual action data, right? So this is a valid call data because this all works. This points to the correct value in the call data. The call data is the correct length. We just have 2 randomly unused 32 bytes that we don't need. But because the contract has this hard-coded value, we can exploit this because it thinks it's going to be there, but it doesn't necessarily have to be there. So let's get into the code and start actually exploiting it. So let's go ahead and start here. First thing is we are going to connect to the challenge contracts. Oh, that's fine. And then we're going to start creating our components of the call data. So essentially what we're going to do is start creating all these components to then put them together to create a transaction to send, right? So we've connected to the contracts. Our first thing is we're going to get the execute signature hash. So this is that function selector, those 4 bytes that uniquely identify the function. So we're going to go to the vault, right? This is this vault contract, to the interface of that vault and get the signature hash. So this is a helper function from the ethers library. So we've got that function signature now. The next thing that we're going to do is add in our target. So this is the attack vault address. And again, we're going to pad it on the left so it goes up to 32 bytes. And this .slice2 at the end will just get rid of the 0x at the start because we're going to start to concatenate this all once we've created all this. So we have the execute, we have the target first parameter. The next thing that we're going to get is the bytes location. Ooh. So again, coming back to our kind of layout of our exploit here, we have the function selector, the target. Now this is the data location. Again, these all need to be 32 byte values. So the 32 byte values, hex 0 pad, we're going to point to hex 80 and again, remove the 0x at the start. Then what we want to do is get the component of the withdraw selector. So this is the function selector for the withdraw function, which is what we are allowed to execute. So this is the kind of fake or dummy ABI that we are putting in. Now, this is kind of like why this challenge is called ABI Smuggling, is because we have a secret ABI that's, built in and all that kind of stuff. So that's why I think the name is called that. The next thing that we have is the bytes length. So in our action data, this is the length of our action data. Now, in this case, it's going to be 0x40. And the reason behind that is because if we have a look at the sweep funds function, where is it? Here. So if we look at how long this data is going to be, it's going to be 4 bytes for the function selector, as in this is the call data for sweep funds, 4 bytes for the function selector, 32 bytes for the address receiver, because that is a known non-dynamically sized type, and 32 bytes for the token, again, a known 32 bytes type. This is just an address, but it's using the interface here. So 4 plus 32 plus 32 is going to give us hex 40. Again, pad to 32 bytes and slice 2. The next thing that we want is the sweep selector. So the selector for sweep funds, again, going to the vault, going to the interface and getting that. And then we're actually just going to grab the sweep funds data. So this is going to be the actual call data that we pass in. So this is going to pass in the recovery address. So again, looking at the parameters for the sweep funds function, we want to send all funds to the recovery address and with that specific token address. So we pass in the recovery address padded 32 bytes and the attack token address padded 32 bytes. Again, slicing 2 off all of this. So now we want to actually generate our payload. So we've got all the components that will build up this. We can just create our payload. So we get the execute function plus the target plus the bytes location. Wait. Oh, this is in the wrong location. No. Why is that offset by 1? Or is this all offset by 1? Okay, good. So our payload is going to be our execute function selector. So again, here, then the target, right? Then the bytes of the action data location, which is this one here. Then it's going to be just a nothing, so random data of 32 bytes. So this is just hex 0 pad of 0 to 32 bytes, slice 2, sorry. Then we're going to add the withdraw selector. So this is this 0xD9CADE1, blah, 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 plus 28 bytes to fill out the rest of the 32 bytes there. Then the bytes length or the action data length, right? Then the sweep selector, so the function selector for the sweep funds, and then the actual data. So now we've got our data. We've created the call data for this exploit. So all we're going to do now is we can just log the data, right? So we can see what it looks like when we actually execute the function. And then we just do player.send transaction to the attack vault address and pass in the payload as the data parameter of that call. So once we've done that, we should just be able to run yarn run ABI Smuggling. And if I haven't made any typos or anything, we should get bingo. So 1 passing. So what happened is we went into the execute function. It read the selector as the withdraw function. It got the action ID given the withdraw function selector and our address that was sending it and the target that we were targeting, so this specific contract. It retrieved that, yes, we are allowed to withdraw. However, when it actually called the action data, it called the sweep funds function. Cool. So that is and then here is the payload here if you're interested in looking at that. That is the challenge. That brings us to the end of the Damn Vulnerable DeFi series. This is challenge number 15 of V3. There may be more challenges in the future, and when they do come out, I will be covering them. But I hope you learned something, and thank you guys for watching, and I'll catch you in the next one. See you.